Can you hear me? Yes, it's a great pleasure to visit Riken for the first time and give a talk here. And I see it's a very fancy talk, and so I'd like to thank Taketo Sana and I'd like to thank the staff at Riken for organizing my talk. The talk is about link homology theories, and I'll target an audience of mathematicians and physicists. So please stop me and ask questions at any time. So the talk is about link homology. Let me go back in time and just remind us that when you have a topological space X, space such as manifold or in CW complex, then one of the first invariants that people discovered of sufficiently nice topological spaces is the Euler characteristic. It is chi of x. And for instance, in case of a surface, if you have a surface, you can triangulate it. You can break it into a union of points, intervals, and triangles, and then you count the number of points minus the number of intervals plus the number of triangles, and you get an invariant of a surface X. And you can generalize to more general. You can extend this to more general topological spaces and get one of the first invariants, chi of x, and for nice spaces, this is well defined and belongs to. It's an integer invariant. And then later, and so again, a long time ago, people discovered that the Euler characteristic is a shadow of a much deeper invariant of topological spaces called homology. Homology, or sometimes cohomology of topological spaces of x. Let's write it as h of x. And this homology, and I hope that you are familiar with homology groups of nice topological spaces. So it's integer graded, so it's a sum of h sub n of x, where n is an integer, and homology groups. And these are abelian groups. Abelian groups. And you can recover the Euler characteristic from the abelian groups as chi of x is the sum of -1 to the n rank h n of x. As long as rank is finite and as long as there are only finitely many non-zero terms, the sum is finite, and this is a way to define the Euler characteristic in a more intrinsic way for spaces that might not have a decomposition into points, intervals, triangles, etc. So this is a more intrinsic formulation of the Euler characteristic, and it extends. So while this is only defined for some spaces, homology is defined for any space, with understanding that this might have infinite rank, or infinite many groups can be non-zero. And the discovery of homology of x it gave the birth of algebraic topology that was led to. I would guess it maybe was about 100 years ago that Poincaré discovered other people with homology groups. And sort of it gives you much more information and leads to a much deeper theory. And in particular, I want to remind you that homology is functorial invariant. So it's a functor. H is a functor. From the category of topological spaces. So the category of, well, what we have here is an abelian group for every n, so we should say category of graded abelian groups. And homomorphisms between them. And this functor to x, it assigns homology groups h of x. And to a continuous map from x to y, continuous map f, it assigns a homomorphism of groups from h of x to h of y. F lower lowest star. So you get information not only about topological spaces, as in this example, but you get information about continuous maps. And you get a functor from this kind of vague, more vague or more complicated geometric topological category to something very, very explicit. And so this has kind of greatly developed into algebraic topology, where people generalize homology to more general homology theories, such as K-theory or cobordisms. They discover homological operations. So there is kind of there's a very deep giant theory that developed out of this construction. And again, I think often in math, often one of the problems is to take some structure, it could be category structure, which is hard to deal with, such as topological spaces and continuous maps, or maybe metric spaces and maps with respect to metric to some degree, and then pull out some more specific information out of it, which often has to be algebraic. And sort of so usually you want to map something more vague, topological, geometric, into something which is easier to manipulate, such as something algebraic, such a number, homology groups, maybe homotopy groups, or pi1 is not abelian, but sort of a lot of mathematics and including algebraic topology is about taking kind of linearizing things, so building some information of algebraic, extracting invariants and information of algebraic origin from something which is harder otherwise to understand. And I think this is also even before algebraic topology, if you just look at the more basic applications of mathematics, a lot of it is just linear algebra. I mean, applications of mathematics in real life to economics, biology, a lot of it is just linear algebra, differential equation, linear algebra. So it's just pulling out some algebraic information from something more vague and more topological. So it's linearization. So passing from a more complicated category to the category of, say, vector spaces and linear maps. And in this example, the category behind homology groups and homological invariants. So here is category of vector spaces and linear maps. And here's the category of complexes of vector spaces. This is where you have a space VI, a space in every degree. And you have a map D squared equal to 0. So D is a differential. And you take homology groups on the D, so you take the kernel, portion of the kernel by the image of the previous D. And so I think a lot of applications of mathematics outside of mathematics is really, it's about this category of vector spaces. And in this example, we are dealing with slightly more complicated category of complexes. And yeah.
So the function where you said that you is the continuous. So it's not necessary to be very smooth nor like.
So there are various definitions of homology groups, and there are several definitions that work for any topological space and any continuous map. So it doesn't have to be smooth. So for smooth spaces, for smooth manifolds, you can use the de Rham complex. You can use the complex of differential forms to write down the homology. Manifold X, you can use complex of differential forms on X with the de Rham differential to write down the homology groups. But there are other constructions available for more general spaces or for other spaces. One of the constructions is using the singular homology. So in some sense, it's probably a bigger complex than the Rham complex, where you look at all continuous maps from an n-dimensional simplex. So delta n is n-dimensional standard simplex. you look at all continuous maps from your simplex into X, very large number of, typically there's a very large number of such maps, X's that we encounter. And given so each of these maps from a simplex into X gives you one generator of the n homology group. So there are as many generators as there are maps. And then on this generator, you define the differential. Differential restricts the simplex to its boundary, its oriented boundary, and sends m to the sum of the maps, one for every boundary n-1 dimensional face of the simplex. So this is this doesn't require smooth structure. This is more general at the cost of having in some sense, even bigger space than space of differential forms.
Also, it doesn't have to be multiple. So, for example, the dimensional x and y can be issued.
Yeah. So that too. So here, X is any topological space, Y is any topological space, F is any continuous map. And then, whenever you have a map of a simplex into X, you can compose with F to get an induced map from a simplex into Y. And this uses a map of complexes from complex of X to the complex of Y, and it induces map on homology. But then you have to do some work. You have to show, so you get some giant complex. But in this complex, it's hard to compute in this complex. So people show that for nice X, there's a much smaller complex of finite rank of homologous groups of finite rank. So if X is built out of points, intervals, two-dimensional cells, three-dimensional and so on. So if it's built from standard pieces, which are cells of various dimension, so X might be a manifold, X might be a singular space, but if it's glued in a standard way, in a nice way from these pieces of dimension 0, 1, 2, then you can show that this very large complex and its homology can be reduced to a very small complex with a basis in this complex given by 0 cells, 1 cells, intervals, etc. So you can show that there is a explicit combinatorial model for a complex giving you the same homology, but which is much easier to understand and manipulate. So I'll tell you about doing something similar where we replace topological space X, replace it by a knot or link L in the free space, where so to a knot L we'll assign homology groups H of L. Of course, there are boring homology groups, because if you have a link L in R3, you can take its complement. The complement is a certain topological space. You can look at R3 minus L. That's an example of a free manifold. And free manifolds have a deep theory assigned, related to them, which goes back at least to the work of Kyriakopoulos in the 1950s. And you get a very deep theory that's been studied over many decades. So somehow low dimensional manifolds are special. So three manifolds and four manifolds, they're special in several ways. And so when people study algebraic topology, they may study manifolds and spaces in all dimensions. And that's one theory. But then we discover that in low dimensions, topology has very special different behavior that is unique to these dimensions. And some people speculated that's because macroscopically, at least on large scale, space-time is four-dimensional. But so who knows? But so for instance, free manifolds, on one hand, you can build lots of them. On the other, they have very rigid restrictions on the fundamental group of free manifolds. And you can think of links as toy models, sort of give you toy models of three manifolds. And the three manifold corresponding to a link is the complement, or 3 minus L. So let me draw an example of this is a not. So it's a link with one component, not L. And let me give you a picture of a link with two components, L. And so again, over the past decades, people discovered that these simple looking pictures, I mean, not sub to equivalence, links up to equivalence of these simple looking pictures and the corresponding three manifolds, they have incredibly deep structures behind them. And usually people just apply, they somehow found ways to take some other theory, maybe differential geometry or representation theory or mathematical physics, and apply it to find structures, new structures that involve nodes. So it's part of this was motivated by classification problems, but to me it's sort of not even the point. I think the point is that if you study these three-dimensional structures, there is an incredible amount of mathematics and mathematical physics related to it for some reason. So you get very, very deep, rich structure behind it. And most of the time, you need to apply something else to nodes and three manifolds. You don't do it by just studying topologically nodes. You somehow take some other theory and it miraculously relevant to the study of nodes and three manifolds. And this is specific to 3 dimensions and into 4 dimensions in some cases. And again, very, very naively, you get a lot of information about not by just taking the fundamental group of R3 minus L. You already get huge amount of information. Of course, these are very special groups. Not any group can have this form, and it carries already a lot of information about nodes. In some sense, you're almost done by working with this group. So in some sense, you don't need all the fancy theory, but just structurally you get, and we'll see an example, you get a lot of things out of it. But, you can, so you can also study 4 manifolds. That's related to 3 manifolds. Again, it's also in some sense you get a special behavior here versus high dimensional story. In high dimensional manifold, they're closely related, but I think this is much better understood. This is maybe gauge theory. I think the main results are one of the main constructions are Donaldson theory, Flory theory, and for 4 manifolds and related to 3 manifolds. So let me, before we get to this, so what I want to do is tell you about this kind of more exotic, strange theory, this kind of exotic homology groups for nodes and links. But before this, let me tell you kind of before this. So I'll first tell you the analog of the Euler characteristic in this case, and Taketa mentioned the Jones polynomial of nodes and links, and that's an example of a so-called quantum invariant. Which is related to Chern-Simons theory on the side of mathematical physics. And mathematically, it's related to representation theory of so-called quantum groups discovered by Jimba and Ginfeld. And this is a pretty fascinating theory where you start with a simple Lie algebra, G, a standard, I mean, the simplest example is SL2. And you study its representation theory. And representation theory of simple algebras has a beautiful, it's deep, beautiful theory. You can classify finding representations of G. So it's absolutely canonical. in its beauty and its application to combinatorics, to geometry and physics. And when you study representations, you can rephrase them as modules over the universal enveloping algebra of G. And in the sphere of quantum groups, and this is an example of a Hopf algebra. And in the sphere of quantum groups, you deform this to more complicated, more subtle Hopf algebras, called the quantum group UQG. And you study its representations, and this gives rise to the quantum invariants of links. And one of the earliest quantum invariants was the Jones polynomial, which can be defined so it can be defined as follows. So if you have a link L, so you have a link, and for convenience we keep track of orientation. So pick an orientation for every component of a link. And to L, there is an invariant assigned to it, which has, let me call it J of L, the Jones polynomial of L, and it takes values in Z, Q, Q inverse, in the ring of Laurent polynomials in Q, within the G coefficients. And again, you can define it in various ways, but a down-to-earth way, so conceptually, you can think of it as coming from representation theory of this Hopf algebra, conceptually, for instance. But you can also define it in a down-to-earth way. You say you want the following condition, that if you have three links that are almost the same everywhere in the free space, but they differ just slightly. They differ very slightly inside the three-dimensional ball. And this is one link, this is another link. So you see that they differ by crossing inside a small ball. And the condition, and the third link is going to be different. And so what we want is a linear relation saying that no matter what's outside of this region, as long as the three links are related in this way inside the three-dimensional ball, then there must be a linear relation on the three Jones polynomials of these three links. And this is a system of infinitely many linear relations, because you're saying that no matter what's outside, this should be the relation on the three links. And you can check that this almost determines this infinite set of conditions. It almost determines the Jones polynomial. You just need you observe that from this condition, by closing up on the side, you can check that the Jones polynomial of a link L union with unlink is going to be the Jones polynomial of L times Q plus Q inverse. So that's easy. That's easy to see. And then you introduce the condition of the Jones polynomial of the empty link when there is nothing is 1. So with the Jones polynomial of a circle is Q plus Q inverse. So this is our normalization for the Jones polynomial. This is one way to define it. But if you want to see where it comes from, then you study quantum SL2 and you study representation theory of quantum SL2. And then in this representation theory interpretation, when you have a crossing, so you use two-dimensional representation of your quantum SL2 that you put at every endpoint. There's V. V is isomorphic to C2 with an action of the quantum group. And you put a copy of V at every endpoint of a diagram. And then to a crossing, you assign a linear map from V tensor V to V tensor V, which respects the action of quantum SL2, which commutes with the action of quantum SL2. And there are not that many maps. In fact, if you just have SL2, then V tensor V, which is V square, decomposes as the second symmetric power of V plus second exterior power of V. Yes.
So D of Q inverse is the integer value of the polynomial of Q1, Q2.
Yes, Z Q inverse. These are Laurent polynomials. Here Q, in our interpretation, Q is a formal variable. Formal variable in the Chern-Simons theory, it's a root of unity. For us, it's a formal variable. Formal variables like X, like variable X. You just take a variable and use its inverse. Yeah, it's like it's just a variable.
And so J takes the value on that integer value to another Q1 inverse, and so how many stations are there? So that's a big simple relation with J.
Yeah. So this condition, it encapsulates infinitely many relations because it says that no matter what's outside, you have three links. This link, this link, and this link, and their invariants should be related in a linear way. So it's not obvious beforehand that this is well defined, but this is consistent. You have to remember that a link can have many diagrams. For instance, this diagram of a link, it defines the same link as this diagram. So topologically, these two are the same. So there's something on the outside, but topologically it's the same link. So it's given, for instance, two diagrams, it's non-trivial to figure out do they represent the same link or not. So there are some subtle questions. So we're saying that one way to see that you get a well-defined invariant is to interpret it using representation theory of this Hopf algebra. So in the Hopf algebra, if you study representations or vector spaces on which this Hopf algebra acts, you can take that as a product. So the properties of Hopf algebra is that you're able, if you have two representations, for instance, if you have two representations of a group, you can tensor them, and you still have a representation of the group. Or if you have two representations of the V algebra, you can tensor them and get a representation of the V algebra. And when you write SL2, it's the first non-trivial simple V algebra. SL2 is the smallest simple V algebra, and it appears everywhere. And this is the first non-trivial example of this theory. So there are just more technical examples for other V algebras beyond SL2. But here, sort of conceptually, where does this, from the representation theory side, where does this relation comes from? It comes from, let me just do, when Q is 1, you just have the usual SL2. And you have the usual SL2, you have this C2 with an action of SL2. You can take C2 tensor C2, so V tensor V. It decomposes into sum of two irreducible representations as 2 of 3, the 3-dimensional and 1-dimensional representation. And so the space of Holmes, the space of intertwiners, Holmes from V square to V square is 2-dimensional because it has to take S2 of V to S2 of V, and it has to be a multiple of the identity on S2 of V. And it's a multiple of the identity on lambda 2 of V. So you get two multiples of the identity. So you have 2-dimensional space of Holmes from V square to V square. And the same in the quantum case. When you Q deform, when you add Q, you still have 2-dimensional space of Holmes from 1 to 1. But here we have 3 maps. You have this map, and this map. So they have to be linearly dependent. And when you do the computation, you can check what these are the coefficients. So this is a conceptual explanation why we have this so-called skein relation. Because just the space of Holmes is 2-dimensional from V square to itself. Yes.
The formula right on this blackboard. Guys, only to 3 months to the case.
Well, this is simpler than free manifolds. It applies to, this is specific for links. This is specific for links in R3.
The videos, another was question for manifold.
Okay. So for free manifolds, you need to do either Chern-Simons theory, where Q must be a root of unity. And then on the level of Khovanov groups, you need to make Q root of unity, so you need to do additional manipulations. This is known as the Witten-Reshetikhin-Turaev theory. So it's more complicated. So for free manifolds, things are more complicated. So links are sort of somehow simpler case. Plus for links, you can use generic Q. You can use Q formal parameter. Okay. Okay, but so there is also this is conceptual. There is a more combinatorial. So our idea is we're going to replace Jones polynomial. We can say that it behaves like the Euler characteristic of some homology theory. So we're going to replace it by homology theory, H of L, and say that the Jones polynomial is the Euler characteristic of this homology theory. But to motivate this homology theory, I want to give you another derivation of this formula due to Louis Kaufman, which also goes back to the early days of the Jones polynomial, and it quickly followed the original Jones approach to his polynomial. The idea is to simplify even further, because if you look here, then these two diagrams, they have roughly the same complexity, because they have the same number of crossings. If something happens outside, then these two diagrams have the same number of crossings. So it's not clear how to, which one is simpler. But Kaufman pointed out that there is a way to have a kind of iterative simplification, which is immediate for these diagrams. And so Kaufman's construction was to I'll do a modification of Kaufman construction, which is slightly less symmetric, but which is more convenient for us. So Kaufman, so he takes link L, he takes diagram D, so planar diagram, such as this two. And at first he forgets about orientations, forget orientations. Without orientation, he wants to assign a Kaufman bracket of D, which also lives in ZQQ inverse as follows. Just a scaled version of the Jones polynomial, but it's as follows. So you require that. So if you have a circle, then the invariant is as before. It's Q plus Q inverse. And if you have many circles, it's Q plus Q inverse to the K, where K is the number of circles. And then if you have a crossing, it's a version of a skein relation. So it's a linear combination. You say that the Kaufman bracket is given by a linear combination, simplifying this way to two arcs minus Q inverse, simplifying this way to arcs. Again, I'm breaking the symmetry of his definition just to make it kind of easier for us later. So he uses Q, square root of Q, and then you can make things more symmetrical. He uses overall minus sign here. But let us do this rule. So this rule, you can check, for instance, that if you take this diagram, like this diagram, you can simplify this crossing, but things will cancel out. So you can check that you get the same answer as for this diagram, which is a good sign, because we want to define the same link. So we want this diagram to give us.
Excuse me.
Question?
Yeah, perhaps for the vertical resolution, there should be Q in the Kaufman bracket.
Here,
For the vertical resolution,
so in Kaufman uses, so his Kaufman's normalization is that minus Q plus Q inverse, and crossing is Q 1/2 plus Q minus 1/2. So I'm just slightly changing to make it easier for me later.
Okay, thank you very much.
This is more symmetric. But so if you can simplify, you can check that this is equal to this, which is what we want. Of course, we want the invariants under moves that don't change the topological type of a link, and you can check that for the so-called randomized 3 move. The invariant is the same. And notice that this is well defined because for each crossing, you're reducing to something simpler, to something which doesn't have this crossing. So these diagrams are intrinsically simpler. They have one less crossing compared to this diagram.
Yeah, this is just Riedmeister smooth type 3, right?
Oh, so these two, so these two are Riedmeister 2 and 3 moves.
Yeah.
And there's also, you can check that, for instance, for yeah, I mean, so if you have, so this is going to be a plus or minus Q. So you can check with this up to some simple scaling, you get the same invariant as here. So the point is that we're sort of ignoring orientations, but we're also in the neighborhood of this statement, because if you put here a V and V, so each of these maps is again an intertwiner from V tensor V to V tensor V. We just sort of need to identify V if it's dual, and there are some kind of issue how you identify, and so that's why this is slightly less intrinsic than this description, but conceptually it's very similar. You're also saying that the space of intertwiners is two-dimensional, so there's going to be a relation on the free intertwiners, a linear relation on the free intertwiners. It's very similar, but it's just kind of simpler in some sense. And so you can check that the Jones polynomial of L is given by taking this sort of decompose all the crossings. In every, you'll have many terms, but every term is a union of circles. So just count the number of circles and convert it to this exponent. So you can check that the Jones polynomial is the Kaufman invariant, Kaufman bracket of a diagram D times -1 to some power and times Q to some power. That's easy to compute from the diagram and orientations, which I'm going to skip. But it's just this way it's easy to check invariants under so-called randomized moves of diagrams that don't change topological type on the link, and it's well defined because every time you reduce the complexity in a kind of strong way. So let us maybe questions. Of this J, so here, so usually people start at first to start with a link or a knot, so it's closed. It's closed. But if you want, you can look at links with boundaries. So link with boundaries, I can say, well, so I have a say plane, so I'm going to look at a link which has boundary. So you can study links with boundary. They're called tangles, and then the invariant of a tangle, it's not just a number. It doesn't live here. It lives in some vector space. And this vector space, and this vector space relates to representation theory of SL2 and quantum SL2, because this tangle gives you a map from a trivial representation C to representation to V tensor N where n is the number of boundary points. So the invariant of a link is going to be a morphism from a trivial representation to this representation. And this morphisms constitute the space of invariants, what people call invariants of V tensor n. So the analog of the Jones polynomial is an element of this vector space.
Yeah, so like looking at the given J of X. So
Yes.
So that contains various homological extension of that. So whereas the most simplest one, so how can we know the number of the closures?
Yeah. So I think if you just set Q equal 1, number of closed loops, you can, the number of components, you set Q equal to 1, and Q equal to 1, you get, so for a circle, you get Q here. So, so J, so J of L is going to be Q to the number of components of L. Yes. Yes. Yeah, this is kind of this first, the simplest specialization, Q equal 1, gives you the number of components. Yeah. Yeah, you get the number of components. Yes. Yeah, but for instance, if you take the trivial link versus the link with a non-trivial linking number, you will also see the difference in the Jones polynomial. And I think you should just expand Q. If you look at Q near 1, look at the first term of the expansion, you should get the linking number. Yeah, people study perturbative expansion of JFL of the Jones polynomial when Q is near 1 in powers of Q minus 1. And this is the so-called the theory of finite type invariance of associative invariance. So it's been studied in a lot of detail. So you get invariants which are repackaged in a different way. You get the Jones polynomial, but rewritten in the perturbative expansion around 1. So those are called finite type invariants. Yes. Yeah, these are called, when you have two circles, these are called two component links. And one component links are called nodes. But the number of components is a very basic invariant of a link. It's like the simplest invariant of a link. And beyond this invariant, you can look, for instance, at linking numbers. You can look at linking numbers. You can draw a surface, oriented surface, which bounds one component and count the geometric number of intersections with the other component. And that's the kind of next level, invariant of the next level. But before the Jones polynomial, people studied more elementary invariants, such as the Alexander polynomial. Alexander polynomial is more in the spirit of linking number and its higher level interpretations, which can be recovered in a simpler way from pi1, from the fundamental group of a link complement. But with the Jones polynomial, these are kind of more subtle invariants that don't come immediately from group theory. Yes. So this is due to Kaufman, and it's just another way to describe the Jones polynomial and see that it's well defined. And so I promised you to lift the Jones polynomial to the homology theory. So that the idea is that you have a skein relation with on 3 terms. And you can just ignore this Q. And then the idea is that this return relation can be lifted to a long exact sequence of homology groups. So the point is to say that we're going to replace the skein relation written there into, we'll have a long exact sequence of homology groups. So to a link L, we now assign homology groups. And the skein relation is going to be replaced by a long exact sequence on these homology groups. So there's going to be something additional about Q. So J of L is in Z QQ inverse. So it turns out that you can, and recall that when we lifted the order characteristic of L, order characteristic of a topological space X to homology of X, this has parameter, integer parameter Hn of X. So here we already have parameter from the start, powers of Q. So it turns out that to a link L, you can assign homology groups H of L, which are now bi-graded, not a single grading, but a bi-grading. So H of L is a direct sum H I J of L, these are integers, such that the Jones polynomial is the sum -1 to the I, Q to the J, rank H I J of L. So the Jones polynomial, it gives you an integer for every power of Q. For every power of Q, you can look at the corresponding coefficient. So it turns out that for each, so you fix J very I, fix J very I, and so you're just taking homology with a fixed J to recall the corresponding coefficient of the Laurent polynomial. So you can sort of imagine that you have a plane, and in the plane with this homology groups Hi J of L, Hi plus 1 J of L, and Hi J plus 1 of L, Hi plus 1 J plus 1 of L, and they extend in 2 directions. And only finally many of them are non-zero. And then, so you take the order characteristic along in the horizontal direction to recall the coefficients of the Jones polynomial. So if you write the Jones polynomial, if you write it as sum A sub J U to the J, rank Hi J of L, rank, yeah, this is the rank, rank of a billion group. A billion groups, so it's like dimension. It's similar to the dimension of a vector space. Yeah, so in other words, so we recall the coefficients A sub J by looking at the groups on the Jth level, and taking the order characteristic along this horizontal line. So then we get J plus 1, you get A J plus 1 as the, so you can sort of bi-grade it. Also similar to Hodge theory in some sense, where you also get bi-graded groups. So the idea is that this skein relation on 3 terms, it should become the long exact sequence of homology groups, because if you have a long exact sequence, then chi of this minus chi of this is going to be equal to chi of this, except that there's additionally Q, which I'm ignoring. There's a Q, and Q becomes additional grading. And sort of it turns out that it works. Maybe I'll sketch I'll sketch how it works. Yeah, so we need to construct. So for instance, if you want to inductively construct homology of the more complicated diagram from homology of simple diagrams, we need to know the homomorphism. So, as you simplify and simplify, so for instance, if you have, let's look at this diagram with a single crossing, right? So we should, it resolves into this diagram and into this diagram. So we need homology of this diagram. Homology, let me move this a little bit. So we need homology of this diagram. And we need a map between them. And then if you have a map, we can extend, we can add the third term, but then we can almost understand the third term if you have a map. So we do need this connecting homomorphisms. Well, need at least this map. So let me adjust these maps to inductively construct the homology of the diagram with more crossings. Let me explain this. So you get connecting homomorphisms, but the idea is to just build this two, build the map between them, and put here the cone of this map inductively. Just put here the cone of this map. So you need at least these two, and you need a map between them, and then you iterate on the number of crossings. And so how do you build this? So when you have no crossings, you just have a circle or several circles, and its invariant is q plus q inverse. So q plus q inverse is you need to have a copy of z in degree -1 and 1. So if you have a copy of z in degree -1 and 1, and if you take take all the characteristic, let's say you're in homological degree 0, you just have this z gives you 1 with q inverse, and this z gives you 1 with q1. So you kind of guess that to a circle, you want to assign just 2 copies of z in these degrees, in degree 0 -1 and in degree 0 1. Okay. But you also need some then to several circles. So when you have, let me call the Sabinian group A. Call the Sabinian group A with 2 z's. So when you have more than one circle, you want to assign to this a tensor power of A. That's A squared, because that corresponds to the invariant of this is going to be q plus q inverse squared. So that corresponds to the graded dimension of A squared. So you kind of guess that for k circles, you assign A tensor k. But you also need some interactions between the tensor powers of A. So for instance, here you have, for the first term, you have A squared. And for this term, you have A. So you need a map between them. Map, which is kind of your, in this map, let me call this map M. It's map M because it looks like multiplication, because you go from 2 copies of A to 1 copy of A. And if you think about it, I mean, there are not that many possible multiplications on an abelian group of rank 2. But so it turns out that you can, what you do, you think about, let me just call a generator of this z1, let me call a generator of this zx. So 1 in degree -1, x is in degree 1. If we shift this 1 degree up, you get 1 in degree 0 and x in degree 2. And this has a multiplication. You can think about z1 plus zx and identify this with cohomology of the 2 sphere. Cohomology of the ring of the 2 sphere. So it has a rank 2 with these generators, and x squared is 0. 0. And so this turns out this is part of the structure. So you take A to be the cohomology of S2 if this basis 1 and x, except that for balance you from degree 0 and 2, you shift the degrees down so that they are symmetric around degree 0. You shift it to minus 1 and 1. Then if you do this, then if you look at the map from A squared to A, 1 tensor 1 goes to 1. 1 tensor 1 goes to 1, so 1 tensor 1 now lives in degree minus 2, and this one is in degree minus 1. So you see that the map does not respect the degree. But notice what we had here, Q inverse, Q minus 1. Q inverse, it tells us that we need to additionally shift the degree down by 1. So we need to shift down by 1. And now the degrees match. So we additionally shift the degree down by 1. And now the sum with differential is getting preserved. Okay. And we know what we want to put here is homology of this diagram. But this diagram is the same, it's a trivial knot, the same as this diagram. So we know that maybe after overall shift, we should get the same answer as just A. And this works just fine because this map is surjective. If you look at the kernel of M, you get basis. So it's x tensor x goes to x squared equals 0. And x tensor 1 minus 1 tensor x. Multiplication takes it to x minus x. That's 0. So these two elements give us the basis of the kernel of M. So sort of size-wise it matches. And then it turns out that you don't need much more. So you just need this cohomology of the two spheres with these relations, x squared is 0. And you also, if you reverse the type of the crossing, so if you look at this diagram, then you'll actually need a map from homology of this into homology of this. So you need the map in the opposite direction. You need a map from A into A tensor 2. So it looks like co-multiplication delta. And that Q inverse gives you additional shift. And that turns out it's not easy to construct, so not hard to construct. To construct this, you realize that A, in some senses, is isomorphic to its dual abelian group, A dual. And that's because this is what people call a Frobenius algebra. Frobenius algebra. It's an algebra with a non-trivial trace. So it's an algebra that's isomorphic as a module over itself. It's isomorphic to the dual module. So I'm going to skip these details, but I'll just say that A is isomorphic to A star. So when you have this multiplication from A squared to A, you dualize it to get a map back from A star to A star squared. Dualize it to get M star. And then this isomorphism allows you to identify A star with A and identify this with A squared. It's like sort of Poincare isomorphism. So all the composing this together gives you a map from A to A squared, which we call delta. And you can also write this delta explicitly. You can compute delta of 1 is 1 tensor x plus x tensor 1. Delta of x is x tensor x. And this turns out to be also part of a structure. So you put here a delta, and you shift the degrees as before. And then turns out that this is already enough to iterate to more complicated diagrams.
Do you have about the kind of do I think homology and
You can think of it this way. You can, yeah, it's essentially, yes, it's, yeah, because it's a manifold, so you can say it this way.
the homology can be calculated by using the differential lines.
Yes.
In this case also you are
Yeah, so I mean, what you're using, so if you have a manifold M of dimension n, if you take Hn of M, let's say that M is oriented, then Hn of M is, let me work over a field, so I'll work over Q, this is Q, and the multiplication gives you a perfect pairing, Hi of MQ, tensor Hn minus I of MQ. It goes into Hn MQ isomorphic to Q. So multiplication homology gives you a perfect pairing. And it allows you to identify this with the I homology.
so find that mapping by using
Yes. Yeah. So you just need to do. Well, you need to use punctuality. So you need to use punctuality, but in the so you probably can. Yeah, I would say it's part of this. I mean, yeah, how to do using different operators. I mean, that's, yeah, one would have to think about this, but I think it's probably standard. I would guess that it's standard way to do it. But so you're using that H star of M for a manifold M. Let me just do Q is the Frobenius algebra. And I mean, part of the story is that this gives you a two-dimensional TQFT. So more generally, when you have a more complicated diagram, so you have a diagram with n crossings, you can resolve every crossing in two ways. So you get kind of many ways to resolve your diagram into diagrams without crossings. And then, so combinatorially, you can just assign, you can build the corresponding tensor powers of A and define maps which are on appropriate copies of A, the M or delta. Then you need to slightly tweak the structure, add minus signs to make every square anti-commute. And so then you sort of collapse this into a single complex. Collapse into a single complex by taking direct sums along the diagonals. Direct sums, and so you get a complex. So from A, diagram D, you build a complex C of D, which is sum of many powers of A. Then the powers of A, one for every simplification, one for every diagram without crossings. So there's going to be 2 covariant such diagrams where n is the number of crossings. And then you take the homology H of D. And this homology of a total complex is essentially the homology we assign to L. H of L. This is a degenerate example because in this example the square commutes for trivial reasons, just because the diagram is very small. But in general, it's more complicated, and the property that you need for this to compute, you need that A is exactly a commutative Frobenius algebra. So A must be a commutative algebra, so multiplication is commutative, and Frobenius means that it has this trace similar to the top degree trace, identification of top degree, homology with Q, making the pairing perfect. This is commutative Frobenius algebras. And such algebras were in a bijection with two-dimensional TQFTs, two-dimensional topological quantum field theories. Topological quantum field theories is a tensor functor from the category of cobordisms in that dimension, in dimension 2, to the category of vector spaces. And they're kind of easy to write down. The properties are easy to write down in dimension 2. It turns out it's exactly a commutative Frobenius algebra. So Frobenius algebra means there's a trace. There's a trace similar to the trace here, which makes the algebra isomorphic to the dual vector space. Making the algebra isomorphic to the dual vector space. And so you can, and then so what's interesting, you get to these homology groups. They are bigraded because you have one direction, the direction perpendicular to the direct sums, but there's also internal direction coming from the homology of degrees of homology of S2 and its direct products, two directions. So you get a bigraded theory. Bigraded. So you need to do some work. You need to check that it's invariant under Reidemeister moves, under the moves that preserve the topological type of a link. But when the theory, but you get some invariants, and then you can check that they have nice factorial properties. But it's not just some random groups; they fit. They kind of extend to interactions between links, and the interactions between links, they turns out they're given by cobordisms. So if you have a link L null, you have a link L1, you have a cobordism S between them. So links are in R3. So this is L null is in R3, L1 is in L3. Cobordism S is in the space one dimension higher, so it should be in R3 times the interval. So think of them as interactions between links, one dimension up. So such a cobordism S induces a homomorphism from, you can check what in this homomorphism from the homology of L1. And you can check what it's functorial, that the composition of the cobordisms correspond to composition of. And so one subtle thing that was always always requires a lot of work is to check what certain sign in this cobordism map is well defined. And so among the many papers of Taketo-sana, so one very interesting work was to kind of a conceptually very simple explanation of how to find this signs and why it's well defined. It's a work from several years ago. But up to sign it's much easier to explain, but sign is very subtle. But so what we get is a four-dimensional theory. We get a 4D theory because now we get an invariant of something four-dimensional of a surface embedded in the four space stretched out between two links. So we get a four-dimensional invariant. So it's not invariant of four manifolds, but it's a sort of some kind of intermediate model, simpler than four manifolds, but it's still four-dimensional. Yeah, so if you look at Jones polynomial, this relates to finite dimensional representation of quantum group UFL2. It's some well-known theory. In particular, it's semi-simple. Representations are semi-simple. But when you categorify, when you extend this to homology groups, so this is in 3D, send to homology, which is essentially a four-dimensional theory due to the extension to cobordism. So it's 4D. There's relation, but here you get into much bigger, even bigger chunk of representation theory relating to many things. For instance, like to highest weight categories of representations of. Sorry, here you have the SL2, but once you lift to homology already for the verification of Jones, you get highest weight categories or representations of GLN for all n. You don't need quantum, you can just do usual, but you have highest weight categories. So with the categories which contain modules like Verba modules, modules of this kind, you need them for all n, but you only need a particular slice. You don't need the whole category. You just need so-called maximal singular or parabolic blocks. So you just need some part of it. And if you want to switch from SL2 to SLK, then the blocks here become less maximal, so they become more complicated. You can also relate to coherent sheaves, Dirac theory of coherent sheaves. So the categories, I mean, once you extend from, if you extend from links to tangles, and you look at the invariant of a tangle in this story, so these are not homology groups, invariants of tangles, they're going to be objects of some triangulated categories. And these categories, so they appear here, appear coherent sheaves on Nakajima, on suitable Nakajima Quiver varieties. And they appear, these categories appear throughout representation theory. For instance, in modular representation theory, various chunks of non-semisimple representation theory, modular representation theory, in many ways, modular representation theory in algebras such as affine Hecke algebras, Ariki-Koike, cyclotomic Hecke algebras, Scalar algebras, Zöger category. So you see them throughout, you see the categories that control this homology and that extend them to tangles. They sort of sit everywhere throughout geometry and representation theory, which is a very, very interesting feature of this story. So you kind of go from this, again, also already beautiful representation theory of quantum groups, finite dimensional semi-simple representations. You go to, when you categorify, you go to this non-semi-simple categories of highest weight representations. So you're dealing with infinite dimensional representations. Or you work with derived categories of coherent sheaves on Nakajima Quiver varieties, or this affine Hecke algebras, Ariki-Koike algebras. Secretly, in many of these constructions, you're doing a categorical version of level rank duality secretly, because you're switching from SL2 to certain pieces of GLN representations for all n. So you're sort of doing categorical version of level rank duality secretly. But there's definitely lots and lots of structures, but also it tells you that in these categories, they control link homology theories, but there are many factors coming from tangles, coming from categorical quantum group actions. So quantum group becomes categorical quantum group. So Ser generators of quantum group, they now become functors. So you get much more structure. And you see things like canonical basis of Khovanov, it becomes a basis of indecomposable projective modules over some algebras. So you see, so this is all related to geometric representation theory, and this was partially motivated by geometric representation theory. And again, this kind of partially answers problems of Crane-Frenkel. So back in the mid-90s, they asked about a codification of quantum SL2 at the roots of unity. That question is still open. There are some kind of various technical issues with codification of Hopf algebras. So that question is still open, but lots and lots of things have been developed since then. But you definitely get lots and lots of story on the representation theory side, on the geometry side. It's a really nice story. And you get lots of functors. You interpret various canonical functors within these categories as functors corresponding to tangles and functors corresponding to categorical actions of quantum groups. Where a quantum group becomes sort of quantum group at the next level, so that EI-FI generators of quantum group become functors. You can compose them. There are natural transformations on composition of those functors. So there's a new level of vision as well. But you see representation theory on both on the 3D level as corresponding to, say, finite representations of quantum groups, and on this level where things are even more complicated. But these are the kind of structures you see at the next level. But all these categories, they have sort of common equivalent subcategories. So the idea is that there are lots and lots of functors relating these categories, or establishing various equivalences between various subcategories. Often you need to take derived category, homotopy category, but so you see kind of you see connections between these categories which are seemingly of different origin. Yeah, you also see instead of coherent sheaves, you can replace it by Fukaya-Floer categories of Lagrangians on the corresponding varieties with a rotated hyperkähler structure. So all of that is present. So maybe I'll stop here. Thank you. Capital.
Can you consider fermionic group and spinning group?
Spin group?
Can be scalar, but can be spinning.
Yeah.
Can you consider spinning group?
Spinning. For instance, there are various equivariant versions of the story where you take S2, but instead of taking the homology of S2, you take various equivariant homology for the group G, which is a subgroup of U2. I don't know if that answers you. I don't know if that's related to the question, but there are, for instance, modifications of the story where you change the homology of S2 into equivariant homology of S2, but I don't know if it qualifies as spinning. But you can, so there is equivariant version.
a different generator, right? So the story
Yeah.
not very different. Maybe not as clear like when one gets a positive differential, because maybe if you have more generators, you have like correct maps.
Yeah, so let me, I mean, to partially answer your question, let me point out that, I mean, for instance, the Reshetikhin-Toraev story V, for any irreducible representation V lambda, we have the corresponding quantum invariant from colored for nodes labeled by lambda. And I just want to point out that in this story, you can get various types of link homology theories, and there's been many developments, many people discovered various theories. The theories with the best behavior under cobordisms, they're known to be for GL, let me say GLN. And when you color components of a link by fundamental representation, lambda A of V, where V is Cn. So these are kind of the best understood cases. And in this theory, the homology of the trivial knot labeled by the corresponding representation, let me say, of quantum group QD4 and lambda QV, the corresponding homology group for the unknot, so this is the simplest knot, is actually ends up being a homology of the complex Grassmannian of 8-dimensional planes in Cn. This is this n. This is the, so already just for the unknot, the cohomology groups are rather complicated. Cohomology of the Grassmannian, the dimension of the cohomology space is n choose A, which matches the dimension of the f exterior power of V. But this is the example where you get the best behavior of cohomology groups, and there are other, for instance, there is the work of Ben Webster, again, also from a while ago, where he categorifies Reshetikhin-Toraev invariants for any simple algebra G and any lambda. But in his construction and in probably related constructions by other people, homology cannot be functorial for some trivial reasons. So there are various constructions which are not functorial, and it's an open problem to modify them to make them functorial, which can probably be also related to the fact that, like in the related story for affine Grassmannian, the sort of corresponding spaces that you see in the affine Grassmannian are going to be singular, unlike this space, which is a smooth manifold. But sort of but you get very complex theory once you go beyond the SL2. So in this best understood case, already for the unknot, you get a very complicated space cohomology of the Grassmannian. So it's a manifold. We have Frobenius algebra structure, so that's all part of the story. But technically, it gets very, very hard, very complicated.
What is the idea or is it that there is really an underlying theory of clarifying this way, or is it more sometimes it will work out, sometimes it...
I think you can trace, I mean, various big chunks of geometric representation theory can be restated, can be refought in this language. But I think it's part of the package that's, that you get some very, very deep, beautiful theory with many facets, which connects lots of mathematics, algebra, geometry, mathematical physics. To me, it's part of the package, which is sort of course, not fully understood. But to me, the important is structural. To me, I mean, not so fine, but it's just that this is a way to uncover new structures, which has many connections to many areas of mathematics and mathematical physics. So to me, it's the structural beauty of the theory that's kind of worth studying. The connection to many fields, and the structures, they're kind of there. Then they're kind of precious, they're rigid, and it's always good to find them. But to me, it's sort of just uncovering new structures, which are, in some sense, I mean, very special. very maybe precious. It's like I can sort of, it reminds me, for instance, people, it's a bit different context. People been studying zygomorphic groups recently and related tensor categories in the work of Andrew Snowden, Nate Harmon, Sophie Chris, and Sophie, in one of her papers, she cited cited Pierre Deligne, who said that these categories, they're like isolated diamonds. They're very hard to find, but they're intrinsically beautiful. And there are not many of them, and they deserve kind of special study. And so this is not exactly the example he had in mind, but it's sort of similar. You get various kind of special rigid structure which connects to many things, and so it's worth studying for that connections. And connection to nodes is just one part of the story. Connections to nodes, to 3D and 4D topology is one part of the story, but there are also connections to representation theory, geometry, mathematical physics, and all of that. So to me, it's this structural richness that's worth studying.
Maybe the question is whether there's a universal construction that works for any Lie algebra.
Yeah, so it's an open problem to, if you look at Webster construction of clarification of Reshetikhin-Turayev invariants for any G and any lambda. Question is, it's an open question. Find a modification of his construction, which is functorial under link abordisms.
So you made an algebra A and out of closed or links, and it turns out that it has a commutative Frobenius algebra structure. And it's natural because commutative Frobenius algebra corresponds to closed topological quantum field theory into to 2D. But I think from TQFT point of view, open string sector is more fundamental, and it's related to symmetric Frobenius algebra, I think. So the question is, are there open string version of the homology theory? And if yes, is it related to symmetric Frobenius algebra?
So my understanding with the system is kind of the most naive interpretation. If you look at, if you look at the, so these algebras are not semi-simple, and I think in TQFTs people often prefer semi-simple algebras, and semi-simple algebras, they're not hard to classify. Very few of them, up to isomorphism in the 2D case. Very few semi-simple algebras, and you can do open case, but it's not by itself. It's not that interesting here. But what you could do, you can extend homology to tangles in a more subtle way, where things are non-unitary, non-semi-simple. It's more subtle extension, but it's not super hard. It's doable. And then you see connection to all these categories and geometry. So there is an extension to the open case. The rest of the links you work with tangles, but it's not exactly. I think it's not exactly open. It's not exactly open string theory. I think it's topological. I think it's kind of something else, but it gives immediately very rich story. I don't know if that's answering your question, but very if you just naively look at semi-simple 2D open closed TQFTs, you do not get anything interesting. And already here things are not semi-simple. This algebra is not semi-simple. So the homology of S2 is not. So again, I don't know if that answers your question.
Okay, thank you.
But you can definitely, there's one way to get into things with boundary, and then it leads you to very rich mathematics.
So I think there are many more questions, but I think it's a good time to wrap up here. So let's thank the speaker again.
Thank you.
So we'll have a casual reception after this. So I think Professor Khovanov will be happy to answer questions. So yeah, let's move on to the reception. So thank you very much for coming today.